At the end of this video, you should be able to list basic SI units and the quantities they describe, convert measurements into scientific notation, and distinguish between accuracy and precision. Chapter 1, Section 2, Measurements and Experiments. Physicists perform experiments to test hypotheses about how changing one variable in a situation affects another variable. An accurate analysis of such experiments requires numerical measurements. Numerical measurements are different than other numbers used in a mathematics class. In mathematics, a number like 7 can stand alone and be used in equations. In science, measurements are more than just a number. For example, a measurement reported as 7 leads to several questions. What physical quantity is being measured? Length, mass, time, or something else? If it is length that is being measured, what units were used for the measurement? Meters, feet, inches, miles, or light years? The description of what kind of physical quantity is represented by a certain measurement is called dimension. You are probably already familiar with three basic dimensions: length, mass, and time. Many other measurements can be expressed in terms of these three dimensions. For example, physical quantities such as force, velocity, energy, volume, and acceleration can all be described as combinations of length, mass, and time. When we learn about heat and electricity, we will need to add two other dimensions to our list, one for temperature and one for electric current. The description of how a physical quantity is represented by a certain numerical measurement and by the unit with which the quantity is measured. Although each dimension is unique, a dimension can be measured using different units. For example, the dimension of time can be measured in seconds, hours, or years. When scientists do research, they must communicate the results of their research with each other and agree on a system of units for their measurements. In 1960, an international committee agreed on a system of standards, much like the one shown on the screen here, which is a standard for mass. They also agreed on designations for the fundamental quantities needed for measurements. This system of units is called the SI system, for System International. In SI, there are only 7 base units. Each base unit describes a single dimension, such as length, mass, or time. The base units of length, mass, and time are the meter, kilogram, and second, respectively. In most measurements, these units will be abbreviated as m, kg, and s, respectively. These units are defined by the standards described in the table on the screen here, and are reproduced so that every meter stick, kilogram, and clock in the world is calibrated to give consistent results. We will use SI units throughout this course because they are almost universally accepted in science and industry. Not every observation can be described using one of these units, but the units can be combined to form derived units. Derived units are formed by combining the 7 basic units with multiplication or division. For example, speeds are typically expressed in units of meters per second, m/s. In other cases, it may appear that a new unit that is not one of the base units is being introduced, but often these new units merely serve as shorthand ways to refer to combinations of units. For example, forces and weights are typically measured in units of newtons, represented by a capital N. But a newton is defined as being exactly equivalent to 1 kilogram multiplied by meters per second squared. Derived units, such as newtons, will be explained throughout this course as they are introduced. Physics is a science that describes a broad range of topics and requires a wide range of measurements, from very large to very small. For example, distance measurements can range from the distances between stars, about 100 quadrillion meters, to distances between atoms in a solid, which would be 0.000000001 meters. Because these numbers can be extremely difficult to read and write, they are often expressed in powers of 10, such as 1 times 10 to the 17th meters, or 1 times 10 to the negative 9 meters. Another approach commonly used in SI is to combine the units with prefixes that symbolize certain powers of 10, as is illustrated on the screen here. The most common prefixes and their symbols are shown on the figure on the screen here. For example, the length of a housefly, 5 times 10 to the negative 3 meters, is equivalent to 5 millimeters, abbreviated lowercase m. And the distance of a satellite, 8.25 times 10 to the 5th meters from Earth's surface, can be expressed as 825 kilometers, abbreviated km. A year, which is about 3.2 times 10 to the 7th seconds, can also be expressed as 32 megaseconds. Converting a measurement from its prefix form is easy to do. You can build conversion factors from any equivalent relationship, including those on the screen here. Just put the quantity on one side of the equation in the numerator and the quantity on the other side in the denominator. Again, as is shown on the screen here. You can see that this is the case for the conversion. 1 millimeter is equal to 1 times 10 to the negative 3 meters. Because these two quantities are equal, the equations at the top of your screen are also true. Thus, any measurement multiplied by either one of these fractions will be multiplied by 1. The number and unit will change, but the quantity described by the measurement will stay the same. To convert measurements, use the conversion factor that will cancel the units that you are given to provide the units that you need, again, which is shown on the screen at the bottom. Typically, the units to which you are converting should be placed in the numerator. It is useful to cross out units that cancel to help keep track of them. If you have arranged your terms correctly, the units you are converting from will cancel, leaving you with the unit that you want. If you use the wrong conversion, you will get units that don't cancel. Measurements of physical quantities must be expressed in units that match the dimension of that quantity. For example, measurements of length cannot be expressed in units of kilograms, because units of kilograms describe the dimension of mass. It is very important to be certain that a measurement is expressed in units that refer to the correct dimension. One good technique is avoiding errors is to check the units in the answer to be certain that they are appropriate for the dimension of the physical quantity that is being sought in the problem or calculation. In addition to having the correct dimension, measurements used in calculations should also have the same units. As an example, consider the figure on the screen here, which shows two people measuring a room to determine the room's area. Suppose one person measures the length in meters and the other person measures the width in centimeters. When the numbers are multiplied to find the area, they will give a difficult to interpret answer, because the units will be in terms of centimeters times meters, as is shown at the bottom of your screen. On the other hand, if both measurements are made using the same units, the calculated area is much easier to interpret because it is expressed in units of meters squared, like would be shown in the bottom of your screen to the right. Even if the measurements were made in different units, as in the example above, one unit can be easily converted to the other because centimeters and meters are both units of length. It is also necessary to convert one unit to another when working with units from two different systems, such as meters and feet. In order to avoid confusion, it is better to make the conversion to the same units before doing any more arithmetic. At this point, you should be able to attempt sample problem A.
Imagine you are buying new carpet for a room. You need to tell the flooring company how much material you will need. The answer can be found by measuring the length and width of the room and then multiplying the two measurements to find the area. If the woman on the left measures her distance in centimeters and the woman on the right measures in meters, we have a problem. The units do not make sense because they do not represent the area the carpet must cover. If both women measure in meters, the answer is much more useful. Now you know how much carpet you will need.
Because theories are based on observation and experiment, Careful measurements are very important to physics, but no measurement is perfect. In describing the imperfection of a measurement, one must consider both the accuracy, which describes how close the measurement is to the correct value, and the precision, which describes how exact the measurement is. Although these terms are often used interchangeably in everyday speech, they have specific meanings in a scientific discussion. A numeric measure of confidence in a measurement or result is known as uncertainty. A lower uncertainty indicates greater confidence. Uncertainties are usually expressed by using statistical methods. Experimental work is never free of error, but it is important to minimize error in order to obtain accurate results. An error can occur, for example, if a mistake is made in reading an instrument or recording the results. One way to minimize error from human oversight or carelessness is to take repeated measurements to be certain that they are consistent. If some measurements are taken using one method and some are taken using a different method, a type of error called method error will result. Method error can be greatly reduced by standardizing the method of taking measurements. For example, when measuring the length with a meter stick, choose a line of sight directly over what is being measured, as is shown in the figure here in portion A. If you are too far to one side, you will likely overestimate or underestimate the measurement, like is shown in part B or C of the image on your screen. Another type of error is instrument error. If a meter stick or balance is not in good working order, this will introduce error into any measurement made with the device. For this reason, it is important to be careful with lab equipment. Rough handling can damage balances. If a wood meter stick gets wet, it can warp, making accurate measurements difficult. Because the ends of a meter stick can be easily damaged or worn, it is best to minimize instrument error by making measurements with the portion of the scale that is in the middle of the meter stick, instead of measuring from the end or the 0 centimeter mark. Try measuring from the 10 centimeter mark. Poor accuracy involves errors that can often be corrected. On the other hand, precision describes how exact a measurement can possibly be. For example, a measurement of 1.325 meters is more precise than a measurement of 1.3 meters. A lack of precision is typically due to limitations of the measuring instrument and is not the result of human error or lack of calibration. For example, if a meter stick is divided only into centimeters, it will be difficult to measure something only a few millimeters thick with it. In many situations, you can improve the precision of a measurement. This can be done by making a reasonable estimation of where the mark on the instrument would have been. Suppose that in a laboratory experiment, you are asked to measure the length of a pencil with a meter stick marked in centimeters, as is shown on the screen here. The end of the pencil lies somewhere between 18 centimeters and 18.5 centimeters. The length you actually measured is slightly more than 18 centimeters. You can make a reasonable estimation of how far between the two marks the end of the pencil is, and add a digit to the end of your actual measurement. In this case, the end of the pencil seems to be less than halfway between the two marks, so you would report the measurement as 18.2 centimeters.
Accuracy is the closeness of measurements to the correct or accepted value of the quantity measured. Precision is the closeness of a set of measurements of the same quantity made in the same way. Consider a game of darts. The target or accepted value is the bullseye in the center. The person who threw these darts is both precise and accurate. All the darts are grouped very close to the bullseye. This graph shows the results of an experiment that was repeated 4 times. Each time the mass and volume of the product were measured. We see that these results are both precise and accurate. They are clustered and very close to the expected value. This set of throws shows that the dart thrower is precise but not accurate. The darts are grouped very close together, but they have missed the bullseye. Here are the results of another researcher's experiments. These results are precise. The data points are clustered close together, but not accurate. Each of these darts landed reasonably close to the bullseye, but the throws are not clustered together and are not precise. In this experiment, the results would average to a value close to the expected value, so they could be considered accurate. They are not, however, precise. Here we have a set of throws that are neither clustered together nor very close to the target. This set of throws is not precise and not accurate. These experimental results, likewise, are not precise and not accurate. When looking at experimental data, precision lets us know the experiment was done carefully in a controlled environment. Accuracy suggests has accounted for all factors that affect the system being studied. Some measuring devices, such as a meter stick, can appear to read different values when viewed from different positions. This phenomenon is known as parallax, and it can be a source of errors in measurement. If you measure the width of this window frame by keeping your line of sight directly over the measurement, you will find that it is 165.2 centimeters long. If you look from the right, you may report a measurement that is too long. If you look from the left, you may report a measurement that is too short.
At this point, you should be able to list basic SI units and the quantities they describe, convert measurements into scientific notation, and distinguish between accuracy and precision.